Structural elements like this steel I-beam carry massive loads, but they have absolute physical limits. To prevent catastrophic buckling and failure, civil engineers must mathematically predict exactly how much internal stress a shape can take before it breaks. This diagram outlines the entire civil engineering landscape. The field splits broadly into two tracks: structural disciplines, which deal with physical frameworks, and non-structural disciplines, like environmental or transportation engineering. Within the structural track, the workflow is strictly divided. First comes analysis, calculating the internal forces a structure must endure. Only after that is complete can we move to design, which is the physical sizing of the concrete or steel. At the very foundation of that analysis branch sits the strength of materials. This is the absolute starting point for calculating internal shear forces, bending moments, and deflections. You cannot safely size a concrete column or a steel girder without first solving for these internal stresses. Analysis is the strict, non-negotiable prerequisite to physical design. To calculate these bending stresses accurately, we first have to isolate a highly specific, idealized physical state, known as pure bending or simple bending. This schematic illustrates how we create that state. We have a standard simply supported beam subjected to two equal point loads, labeled W, positioned symmetrically. Looking directly below at the shear force diagram, notice the zone between points C and D. The shear force drops exactly to zero. There are no vertical sliding forces acting on the cross-section in this central span. Simultaneously, on the bending moment diagram, the bending moment in that exact same span forms a perfectly flat, constant plateau. Within this pure bending zone, we will derive the mathematical equation governing the stress, physically locate the neutral axis, and apply these rules to complex composite beams. By isolating a length of the beam with zero shear force, all structural deformation is driven exclusively by the bending moment. This isolation gives us the perfect environment to build an exact mathematical model of internal stress. Real-world materials contain microscopic flaws and unpredictable variations. To build a reliable mathematical model of simple bending, we must constrain the physics using specific theoretical assumptions. This schematic outlines the constraints of simple bending. The material is perfectly homogeneous and isotropic. The beam is initially straight. Inside, longitudinal filaments expand independently. Most critically, plane transverse sections remain perfectly plane, keeping the grid straight even as the beam arcs. Because the cross-section remains flat and simply rotates around an axis, the longitudinal strain must vary perfectly linearly as you move away from the center of the beam. Without the plane section rule guaranteeing linear strain, the mathematics would break down. It provides the necessary geometry to derive a universal equation for internal bending stress. When a beam bends, the top layers compress and the bottom layers stretch. Between them lies the neutral axis, the specific longitudinal layer where bending stress and strain are exactly zero. This block shows compressive forces in orange, tensile in blue. For static equilibrium, total axial force must sum to zero. We calculate this by integrating stress over the area. Substituting stress with vertical distance y leaves us with the integral of yda equals 0. In mathematics, the integral of yda is the first moment of area. For the first moment of area to equal 0, the axis of reference must pass perfectly through the centroid of the shape. Because the first moment of area must be 0 for equilibrium, the neutral axis is mathematically forced to pass directly through the geometric centroid. This gives engineers a fixed, reliable origin point to measure all stresses against. This graphic displays the bending equation.
The first ratio pairs applied external bending moment, m, against the moment of inertia, I. The second equates internal bending stress, sigma, at a specific distance, y. The final ratio relates stiffness, Young's modulus, E, to the radius of curvature, r. Because stress scales proportionally with y, the stress is always 0 at the neutral axis, and it reaches absolute maximum compressive and tensile peaks at the furthest extreme top and bottom fibers. This equation elegantly unifies the applied external forces with the internal material stiffness and cross-sectional geometry into a single perfectly balanced framework. This matrix defines section modulus, Z, defining flexural strength. Its moment of inertia divided by extreme fiber distance, Y max. Symmetrical shapes have a dead center neutral axis, yielding a single z value. Unsymmetrical shapes, like this triangle, shift the centroid, creating two different y-max distances. This illustrates the moment of resistance. For equilibrium, internal resisting strength must match the external load. M equals sigma max times z. For a fixed maximum stress, a beam's safe carrying capacity is dictated entirely by its section modulus. The strict goal of structural optimization is to move material away from the zero stress zone near the centroid, placing it as far out to the high-stress extreme fibers as possible. The classic I-beam is the physical manifestation of this principle. It maximizes the section modulus, achieving the highest possible flexural strength with the absolute minimum amount of material. In practice, engineers frequently encounter composite or flitched beams, where a weaker bulk material like wood is reinforced with plates of a stiffer material like steel. Because these materials are bolted or glued tightly together, they are physically constrained. As the load is applied, both materials bend with the exact same radius of curvature, creating a single, continuous, straight strain profile across the entire cross-section. While their strain is identical, their internal stresses are completely different. Because steel has a much higher Young's modulus, there is a massive discontinuity in the stress distribution exactly at the boundary where the wood meets the steel. To solve this, we use the modular ratio, represented by M. It is simply the ratio of the stiffer material's Young's modulus to the weaker material's modulus. By multiplying the actual width of the stiffer material by the modular ratio, we convert it into an equivalent width of the weaker material, expanding the cross-section mathematically. The modular ratio transforms a complex multi-material cross-section into an equivalent single material shape, which can then be solved using the standard bending equation. To tackle structural engineering exam problems, you must apply these derivations systematically across two primary workflows, one for single material shapes and one for composites. For standard shapes, follow a rigid four-step process. First, locate the geometric centroid. Second, calculate the moment of inertia using the parallel axes theorem. Third, identify the extreme fiber distance, y max. And fourth, apply the bending equation. When dealing with unsymmetrical sections like T-beams, always test the larger y distance from the shifted centroid. That furthest fiber will always experience the absolute maximum stress and dictate your failure point. For composite problems, the rule is strict. Never analyze the materials separately. Always calculate the modular ratio first, construct the equivalent cross-section, and solve the system as a unified whole. Every calculation traces back to one foundational relationship. Whether you are designing a residential wooden floor joist or a massive steel highway girder, structural strength is determined by geometry as much as material. It requires the mathematical mastery of distributing mass to perfectly manipulate the bending equation.